Hi everyone, and welcome to my talk, The Singly Charged Scalar Singlet as the Origin of Neutrino Masses, which is based on a paper with the same name that we recently published in JHAP. Before I start, I would like to say thank you to the organizers of WIN 2021 for the opportunity to contribute to the workshop. And I would also like to acknowledge my collaborators, Michael Schmidt and Juan Herrero Garcia. I want to talk about the extension of the standard model by a scalar particle, which I call H, that is a singlet under the strong interactions and the weak interactions, and that carries 1 unit of electric charge. The goal is to make statements about the generation of Majorana neutrino masses in this setup in a model-independent way. So here you can see the Lagrangian of the theory. You have the standard model Lagrangian, you have the kinetic term and the mass term for H, and you have this coupling of H to 2 left-handed lepton doublets, which is the only renormalizable coupling of H to standard model fermions. And quite importantly, the conservation of lepton number is respected by all the renormalizable terms in this theory. And thus one can assign units of lepton number to the leptons and to H, as can be seen here. Due to the way the 2 left-handed lepton doublets are contracted in weak isospin space, the associated coupling matrix has to be antisymmetric. Therefore, it always features a non-trivial eigenvector with the vanishing eigenvalue. For our analysis, the only assumption was that when the main contribution to neutrino masses is generated, we require that either one of the neutrinos on the external lines couples via YH to the associated Feynman diagram, while the other neutrino couples differently, which we call the linear case, or we require that both of the neutrinos on the external lines couple via YH, what we call the quadratic case. And I hope that these designations become clear soon. In the linear case, the generation of neutrino masses proceeds schematically, as can be seen here. The black dot is the coupling YH, and the dashed line is the H propagator. And all the rest of the interactions, which are involved in the generation of neutrino masses, are symbolized by this gray blob. And I want to be as agnostic about what's going on here as possible. I only have to assume that there's a source of lepton number violation, because otherwise one that doesn't get neutrino masses in the Majorana case. And there has to be at least 2 insertions of the standard model Higgs web to generate the Weinberg operator. And then the resulting neutrino mass matrix will just be given by X times YH, where X is a matrix that encodes all the information about what's going on in the gray blob. And since the neutrino mass matrix has to be symmetric in the Majorana case, one also has to add the transposed version of that contribution. So neutrino masses are linear in YH, and this is why we call it the linear case. One immediate consequence is that since we do not specify X further, the determinant of the neutrino mass matrix will in general not be 0, and therefore all 3 neutrinos receive masses in the linear case. And now one can take this equation for the neutrino mass matrix and multiply it by the eigenvector VH from the left-hand side and the right-hand side. And then one obtains 0 on the right-hand side, because one always hits one of the matrices YH here, and the eigenvalue is 0. One can realize the gray blob in a model-independent way via an effective operator at dimension 5, which violates lepton number by 2 units and which is suppressed by a large scale lambda. And then the neutrino mass matrix will be approximately given, as can be seen here. Since neutrino masses will be generated at 1 loop level, one has this factor 4 pi squared in the denominator. And since one of the insertions of the standard model Higgs web will be associated to a chirality flip on an internal line, neutrino masses will be proportional to the masses of the charged leptons in the standard model contained in the matrix YE. And the components of the matrix C, of course, depend on the underlying physics, which gives rise to this operator. This expression is only approximately correct, for instance, because there will most likely also be a loop function, which is not explicitly stated here. But in principle, one can compare this structure to what is known about the neutrino mass matrix based on experimental data. In terms of concrete models, one can realize the linear case, for example, via the well-known Z model, in which the particle content of the standard model is enlarged by H and a second Higgs doublet. And then the conservation of lepton number is violated by this vertex here, coupling H to the two Higgs doublets in the theory. In fact, if one integrates out the second Higgs doublet, now one retrieves this effective operator just introduced. A slightly more involved example would be the generation of neutrino masses at 3-loop order, with the particles running in the loops assigned to larger representations of SU2 weak isospin. But in order for the classification in terms of the linear case to apply, the details of the loop structure are not relevant. In the quadratic case, both external neutrinos couple via YH. And here, this unspecified lepton number breaking physics gives rise to a matrix that has to be symmetric and that we call S. And now neutrino masses are quadratic in YH. And due to the symmetry of this matrix YH, the determinant of the neutrino mass matrix vanishes by construction. And therefore, one of the neutrinos will always remain massless at leading order in the quadratic case. And now it's sufficient to multiply this equation by the eigenvector just from one side in order to obtain 0 on the right-hand side. In the quadratic case, it's also possible to realize the gray blob in terms of an effective operator at dimension 5. And then the resulting neutrino mass matrix will be quadratic in the charged lepton masses, since here both of the insertions of the standard model Higgs wave will be associated to chirality flips on internal lines. And since neutrino masses are generated at 2-loop level, we get the factor 4 pi to the 4th power in the denominator. In terms of concrete models, an important realization of the quadratic case is given in terms of the well-known Z-Babu model, which features a doubly charged scalar singlet K, the coupling of which to H then violates lepton number. And upon integrating out K, one retrieves this effective operator just introduced. Another example is the KNT model, or Krauss-Nasri-Trodden model, which features 2 copies of H, one of which is charged under a Z2 symmetry, and a neutral fermionic singlet, which is also charged under Z2. But as in the linear case, in order for the classification in terms of the quadratic case to apply, the details of the loop structures are irrelevant. We derived these expressions in the light blue box, which directly relate the couplings of H contained in the eigenvector to measure data on the neutrino mass hierarchy in mixing, contained in matrices M diagonal, which contains the mass of the 3 active neutrinos, and the PMNS matrix U. And we interpret these equations as conditions that necessarily have to be satisfied for the correct description of neutrino masses in our setup, which is the standard model extended by H and a source of lepton number breaking. Importantly, these constraints are not sensitive to the details of how lepton number is broken, because this was parameterized by the matrices X and S introduced beforehand, and they have dropped out here. So the constraints are actually model independent. So let me now try to explain how we solve these constraints by looking at the quadratic case. So here one obtains 2 non-trivial complex conditions, or 4 real ones equivalently, for either neutrino mass ordering. And I explicitly stated these conditions here on the slide. They have in fact been discussed in literature already in terms or in context of the Z-Babu model, but in fact they hold more generally. So on the right-hand side, the expressions are determined in terms of experimental data, and therefore we assigned pseudo-random variates from normal distributions to the parameters occurring in there. And the mean values and standard deviations of these normal distributions we took from the latest fit results provided by the new fit collaboration in 2020. This is how we varied the right-hand side. On the left-hand side, one has 6 parameters, 3 couplings and 3 phases. And we only had to vary 2 of them since the other 4 are fixed by the constraint. In principle, this works the same way in the linear case, but there one just obtains one quite lengthy complex expression, as can be seen on this slide. And it's not that instructive to look at it, but one notices that here the constraint also depends on the individual neutrino masses M1, M2, and M3, as well as on the Majorana phases eta 1, eta 2. For the presentation of the results of solving these constraints, we chose to show only the ratios of coupling magnitudes because the absolute values of the couplings themselves are not directly determined by the constraint. And one can see that apparently a quite non-trivial shaping of the parameter space available for the couplings is obtained upon imposing the constraints. In particular, large hierarchies among the coupling magnitudes are disfavored. Let me explain the colors which occur here. The small brown area in parameter space indicates where one can find viable solutions to the constraint in the quadratic case, which is a very predictive scenario due to the fact that here the constraint is to a good approximation controlled only by the leptonic mixing angles, which are quite precisely determined by now. And if then one moves on to the linear case, a lot of viable parameter space opens up. The linear case is depicted by the blue and black sample points, the distinction of which is of no direct physical relevance and can essentially be disregarded. This scenario is less predictive due to the fact that the constraint here is controlled by a larger number of parameters. But we found that now it is possible to also explain anomalies related to the apparent violation of lepton flavor universality that have recently attracted attention in the literature. Anomalies here refers to both the so-called Cabibbo angle anomaly, related to tensions in the results of obtaining or determining the US element of the CKM matrix, and apparent deviations of the rates of charged leptons decaying into lighter charged lepton and 2 neutrinos from universality. And the associated parameter space is indicated by the red sample points. So here a further assumption had to be made, namely that we took the singly charged scalar singlet to be the sole driver of explaining these anomalies, basically via contributions to G Fermi, whereas further exotic particles that of course can be involved in the generation of neutrino masses, we assume to explain these anomalies only to a negligible extent. And under this still fairly general circumstance, we found that the simultaneous explanation of neutrino masses and these anomalies at 1 sigma is possible only in the linear case, but not in the quadratic case, because red sample points are well separated from the small brown regions. Okay, let me leave you with the takeaway message, which is that we managed to derive constraints for the couplings of the singly charged scalar singlet, which are model independent, just based on the structures of the neutrino mass matrix. Let me re-emphasize that our classification can be applied to several well-known models of neutrino mass generation, including their variants, in full generality, actually. Okay, thank you very much for watching the talk, and I'm very happy to take feedback. Cheers.